All right. This means that the derivative of f of g of x is equal to f prime of g of x times g prime of x. All right. And this is the chain rule. We call it the chain rule. And I hope you at least were able to follow how we derived it. And even if you don't remember, even if you couldn't recite it off the top of your head, I at least want you to go like, okay, well, I listened to Dylan say it. I agree with it every step of the way. So I know it's valid. And now I can use it knowing it's valid. It is a lot to remember. So I don't like, it's not important to remember how to derive it. It's just important to understand that it's valid. We cool with that? I cannot hear you guys. Can you guys hear me?
Yeah, cool. Sorry, I thought I unmuted. Yeah, I'm cool with that.
Okay, cool. Awesome. So just because this is kind of weird, I'll give you an example. Actually, we'll do a little fun example. Let's say we wanted to find the derivative of x to the fourth plus 5 squared. Wouldn't you agree that this is just sticking this function inside of the function x squared? You're taking this function and sticking it inside the x squared function.
Yep.
Cool. So if we wanted to find the derivative of this, all right, we would say, well, this is a function in the form of f of g of x, where f of x equals x squared, and g of x equals x to the fourth plus 5. Because you're taking g of x and sticking it inside the f of x function. Do you guys see that?
I do.
So the chain rule tells us that it's going to be the derivative of f prime of g of x. And what that means is if f prime of x equals 2x, right, because the derivative of x squared is 2x, then the derivative f prime of g of x, what that means is 2, but instead of an x, you put x to the fourth plus 5. Does that make sense? If the derivative...
Yeah.
Sorry, say that one more time.
Yeah, I think that makes sense to me.
Cool. All it's saying is that if f prime of x is 2x, then f prime of g of x is just 2 times whatever g of x is. In this example, x is our input, right? But in this example, g of x is our input. So instead of doing 2 times x, we have to do 2 times g of x because x is no longer our input here, g of x is. Cool?
Yep.
And then we have to multiply that by g prime of x, the derivative of this function, all right? So this requires the power rule and the sum rule, all right? So the sum rule tells us that the derivative of this is going to be the derivative of this plus the derivative of this, right? So I'll do a little pop quiz. What's the derivative of this? We would know how to do it with the power rule. If it's hard to remember, that's okay because we just derived it today.
Oh. All right. Wait, so we're finding the derivative. So fx is equal to its squared. So we're finding the derivative of what's written on the bottom, or?
Yeah. So remember, the chain rule tells us that the derivative is f prime of g of x times g prime of x. That's the chain rule. So we said that f prime of g of x is this. So the next thing we have to do is multiply it by g prime of x.
And that would be adding 4x cubed.
Exactly. So 4x cubed. All right. So I'll explain in just a second, Henry. So the power rule tells us that if we take x to the n, right, the derivative is n x to the n minus 1. So the derivative of this is 4, because that's our n value, times x to the 4 minus 1, which is 3, 4x cubed.
Yep.
But then the sum rule tells us we have to add the derivative of this, right?
Yep.
But what's the derivative of a constant or a number?
0.
Exactly. So the only thing we're multiplying by is 4x cubed. So this would be the derivative of this function. And in my opinion, I think it's cool because before today, you didn't know how to calculate you only knew how to calculate the derivative of x squared, right? Now you can calculate the derivative of a weird function like this, which I think is pretty cool.
Yes, sir.
Yep. Awesome. All right, let me go back to here. All right, so I did not gauge the timing well. I expected that we would get through these and then do another like couple slides, but that's obviously not going to happen. So we have two options. I could either go through these last few rules, which is just the quotient rule and the product rule for negative integers. The quotient rule will take, I would say, about as long as the chain rule did, and the product rule for negative integers will take a minute. So if you guys want to do that to get all these rules out of the way, we could do that. But also, if you guys are kind of gassed, we could put it off for tomorrow.
What do you want to do, Ryan?
I'm fine with either.
Maybe let's finish this up just to get the rules out of the way.
Cool. Yeah, I think that's a good idea. All right. Let's do the quotient rule. I'm thinking of how I want to do this, because there's many ways to prove it. All right, we're going to do something very quickly. All right, I'm going to show you what the derivative of 1 over x is, just very quickly. I won't stop too much, because I just want to get it done very quickly. All right, so the limit definition tells us it's going to be the limit as h goes to 0 of 1 over x plus h minus 1 over x over h, right?
Yeah.
To get a common denominator up here, I'm gonna do the following. I'm gonna multiply the first fraction by x over x, because that's just 1, so we're not changing the fraction. I'm gonna multiply the second fraction by x plus h over x plus h, because it's going to be 1 over 1, doesn't change it, right? So you agree that this is the same thing. We haven't changed the top thing, because we've multiplied it by 1, basically, on both fractions.
Yeah, I agree with that.
Cool. We have a common denominator, so we can combine these fractions. We get x minus x plus h over x times x plus h divided by h. So if we divide by h, we can add it to our denominator. You agree?
Yeah.
Cool. So if we have x minus x plus h, that's going to be x minus h, right?
Yep.
You distribute the negative. So we get x minus x is 0, so we get negative h over x times x plus h times h, right? We have an h up here and an h down here, so they cancel. So then we get negative 1 over x times x plus h, right? Good with that?
I'm good with that.
Cool. So the limit as h approaches 0 of this, you'd agree, well, as h approaches 0, this term just becomes x, because the h goes away, it becomes 0. X plus h, 0 goes away. Cool. Okay. So then that means that the answer to our limit is negative 1 over x times x, right? Which is negative 1 over x squared. And that's the derivative of 1 over x. Cool with that?
I am cool with that.
Awesome. So the next derivative rule is going to tell us how to find the derivative of when you take a function and divide it by another function. Go figure, right?
Yeah.
All right. So we're going to do it in the following way. We're going to elucidate the chain rule, this derivative, and the product rule to prove the quotient rule, which sounds like a lot, but I promise you it won't be. All right. So I hope you agree. We could rewrite f of x over g of x as f of x times 1 over g of x. Right?
Yep.
Cool. So then the derivative of this is the derivative of this.
Yeah.
Cool. Can I clear the frame? Are we good with that so far?
Yep.
I can't go. It won't let me make any more slides. That's why I have to clear the frame. All right.
I'm okay with that. Yeah.
So then if we want to find the derivative of f of x over g of x, we could find f of x times 1 over g of x. And the product rule tells us this is going to be the derivative of the first one, f prime of x, times this function, 1 over g of x, plus the derivative of 1 over g of x times f of x, right? You'd agree this is what the product rule is telling us, that the derivative will be.
Yeah. Yep.
So we're pretty much done. The only thing is we're left with this, and we have to find out what this derivative is. And wouldn't you agree this is just an example of the chain rule, where we have f of g of x, where f of x is 1 over x, and g of x is just g of x. You're sticking in g of x to 1 over x. You're putting g of x inside of this function. Would you agree?
Yeah. Yep.
So the chain rule tells us, well, then we know how to find the derivative of this function using the chain rule. Handy dandy. All right. So this means that the derivative of this is going to be f prime of g of x using the chain rule. And remember, the derivative of 1 over x is negative 1 over x squared. And because we're taking g of x as our input, we have to put g of x squared instead of x squared, right?
Yep.
Cool. And then we have to multiply it by the derivative of g of x, all right, which is just g prime of x. Cool.
Wait, rewind the past like 20 seconds.
Okay, awesome. So the chain rule tells us that the derivative of this is going to be f prime of g of x, and so it's the derivative of 1 over x, but instead of an x, we have a g of x. That's what this is saying. And remember, we said the derivative of 1 over x is negative 1 over x squared. So f prime of g of x is negative 1 over g of x squared.
Okay, yep.
And then the chain rule tells us we have to multiply by g prime of x. So then that's what we're doing here. We have to multiply this by g prime of x to get this derivative.
Okay.
Cool. All right. We good with this?
I'm good with that.
Awesome. So then we get, well, then the derivative of our original function, what we're at so far, is it's equal to f prime of x times 1 over g of x minus 1 over g of x squared times g prime of x times f of x. This is the last equation we had. All right. Is it clear where these came from?
Yeah, I think so.
Okay. Yet again, remember that we rewrote this as f of x times 1 over g of x. This allows us to use the product rule. The product rule tells us that it's going to be the derivative of the first one times the second function. That's what this term is. Plus the derivative of this function times this function. And remember, we said the derivative of this function is this. So we're basically just replacing the derivative of this function with the derivative we calculated. So that's why the entire derivative using the product rule and finding the derivative of this is this.
Okay.
If it's still not clicking, just let me know. And
It's like a little fuzzy, but maybe I think if you maybe continue, I'll just kind of figure it out.
Okay. And worst case scenario, we can backtrack, and you can always reach out to me. All right. So let's do some simplification. F prime of x over g of x. All right. This is equal to f prime of x over g of x because you're multiplying by 1 over g of x. We can simplify this to minus because we take these two things and we put it in the numerator because we're multiplying this fraction by this. Would you agree?
Yeah.
So then we get minus g prime of x, f of x, over g of x squared, right?
Yeah.
And if we want to combine these fractions, we can multiply this fraction by g of x over g of x, right? Because that's just multiplying by 1. So we'll get a g of x on the top and then a g of x squared on the bottom because we're multiplying g of x by g of x on the bottom.
Yep.
Cool. We can combine the fractions. we get then f prime of x times g of x minus g prime of x. You know what? I'll close the frame so I can just write it. We get f prime of x, g of x, minus g prime of x, f of x over g of x squared. And this is the quotient rule. All right. Tells us the derivative of f of x over g of x is this. And we just showed why that's true. Yet again, you don't have to remember the process. I just hope you now understand why the quotient rule is valid.
Yeah.
Cool. All right, that was the last major one. The next one is going to take like 2 minutes.
Wait, can I just write this down for a second?
Of course, of course.
Okay, I'm on good.
All right, Ryan, you get it?
Yeah,
All right.
yeah, I'm good.
All right, so power rule for negative integers. Remember the power rule we showed only worked when our exponent was a positive integer. We're going to try and see if we can find a power rule for when n is a negative integer. So for example, 1 over x squared, because if we have x to the negative 2, that's equal to 1 over x squared. So we're trying to find a power rule formula for when our exponent is a negative integer. You guys kind of get the framework?
Yep.
Cool. All right. So I could say, and I have the proof written here, I just want to make sure that I'm following it properly. If n is a negative integer, all right, then it's equal to negative m, where m is a positive integer. For example, if n was negative 2, this is equal to negative 2, where m is 2 and n is negative 2. Right? You kind of see what I'm saying?
Yeah.
We could rewrite a negative integer as just a negative positive integer. It's pretty self-explanatory, right?
Yeah.
All right. So then I could say, well, the derivative of x to the n, all right, is equal to the derivative of x to the negative m, right? Because n is equal to negative m.
Yeah.
Cool. Awesome. So then I get, well, then the derivative of x to the negative n is the same thing as the derivative of 1 over x to the m. Is that cool?
Yep.
All right. And I think what it tells us to do is use the quotient rule. All right. We can use the quotient rule here. So the quotient rule tells us that we're going to, if we want to find the derivative of this over this, we take the derivative of the first one, which is 0, times the second function, minus the derivative of the first one, which is the power rule tells us that because, remember, we said m is a positive integer. Do you remember that? We said if n is a negative integer, that equals the negative of a positive integer. So m is the positive integer.
Yep.
And we know the power rule works for positive integers, so we can say the derivative of this is mx to the m minus 1 from the power rule times the original function, which is 1. All right?
Yeah.
Cool. Then we have to divide it by this function squared, which is x to the 2m. Remember when you take something and you square it, you can multiply it by the exponent?
What?
Sorry. So remember, we have to divide it by this function squared, right? X to the m squared.
Okay.
Do you remember the rule where if you raise a number to an exponent and then raise it to another exponent, that's the same thing as just raising it to the...
Yeah, definitely.
Okay, cool. So that's all I'm writing. I'm just writing x to the 2m instead of this.
Okay, gotcha.
All right. So we have this. All right. The quotient rule tells us that this is what our derivative is going to be. You follow that?
Yeah.
Cool. 0 times anything is 0, so we ignore it. We get negative m x to the m minus 1 over x to the 2m. All right. And what can you tell me if we have an x, if we have, like, actually, let me just backtrack. If we have x to the a divided by x to the b, what is the exponent rule for this?
X to the a minus b?
Yes, exactly. Do you guys remember that rule?
Yeah.
Cool. So I have an x to the m minus 1 on top and an x to the 2m on the bottom. So I could rewrite this as negative m x to the m minus 1 minus 2m. Would you agree?
Yep.
Cool. So I'll rewrite that in a bigger writing. Negative m x to the m minus 1 minus 2m. M minus 1 minus 2m, right? So we have an m and a minus 2m here. So we end up getting negative m minus 1, right?
Yeah.
Cool. So our answer is negative m x to the negative m minus 1. That's our derivative. But we said n is equal to negative m, right?
Yeah.
So we could rewrite this as n x to the n minus 1. And then that would be our derivative.
Word. Okay.
Isn't that cool?
Yeah.
So we've shown that the power rule is the same for negative integers, which I think is a pretty cool coincidence. This is the same rule as the positive one, which is cool, which is great.
Perfect.
We cool on how that works?
Yeah, I'll give that one like a 78%.
Okay.
Again, just because of how much stuff is going on.
Yeah, okay.
So I got a little lost in there, but like
yep.
the ending checks out.
Okay, cool. If you want to reach out to me, I can provide more explanations. There's definitely a lot of cool videos I could show you. But all I need you fine with is at least, like, you might forget the process, and if I asked you to derive it on your own, you'd be like, I don't know how to do it. I just want you fine with like following my logic, and then at each step going like, okay, this makes sense. Okay, this makes sense. Okay, this makes sense. So as long as you remember saying that you're fine with each step, then you realize, well, then what Dylan just did is valid. So I know the equation is valid.
Yeah.
That's all I really care about. I just want you to know that the equation is valid. I don't want to give it to you and then you use it. Even if you couldn't derive it yourself, I just at least want you to know that it's valid.
I like that. Yeah, I know that it's valid. Yeah.
Okay, cool. Then that's all we need. Conveniently, we'll get into this tomorrow. The power rule in general, if you take x to any number, this could be x to the 1/2, x to the pi. The power rule is the same. Isn't that a really weird coincidence?
Wait, say it again.
So we're gonna discover this tomorrow. That x, the derivative of x to the n, where x can be anything. X doesn't have to just be an integer, a positive or negative integer. We're going to discover that the power rule for x to anything, so like x to the 1/2, x to the pi, x to the whatever, the power rule is still n times x to the n minus 1. So the derivative of x to the pi is pi times x to the pi minus 1 power. So the power rule is the same.
That is cool.
Yeah, so I think it's cool. I think it's a really weird coincidence, but I think it's really cool. And we'll explain why it's true tomorrow.
Yeah.
Cool. So I didn't get through everything, but that's because I planned it poorly. Tomorrow my plan for tomorrow is we'll take 2 more days with derivatives. Tomorrow we'll finish what I had planned to finish today, which is we're gonna learn the derivatives of trigonometric functions. We're gonna learn what the derivative of sine of x is and stuff like that. And we're also gonna learn what are we gonna learn? We're going to learn some new terminology. Here, I'll preview it very quickly, actually. We're not going to do it right now. Obviously, we're going to do it tomorrow. But I'll preview what we're going to be doing. We're going to be beating a dead horse again and talking about velocities of terminology, velocity again, this topic, derivatives of trig functions, more trig stuff, a different way to express derivatives. We're going to review the chain rule because it's very important. And we're going to talk about peeling the onion, about how, even though this is a hard function, by the end of tomorrow or by the end of the next day, you should hypothetically be able to find the derivative of this function, even though it's complicated and you might need to look at your notes over and over and over again to find the rules. We're going to show how finding the derivative of an insane function like this is just using our rules over and over and over again, like peeling back the layers of this function like an onion and using our rules. So if that doesn't make sense now, it will tomorrow. I promise.
Okay, I think I even get that now. Yeah.
Cool. So then this is what we're covering the day after. We're going to be covering the derivatives of log functions, exponential functions, the inverse trig functions. Remember those? You remember those bad boys? We're going to be finding the derivatives of those.
Oh boy.
And the power rule in its full form. We need another differentiation technique to prove the power rule in its full form, which is that it doesn't matter what n is; it can be anything. And that technique is called implicit differentiation, which is a really useful tool in math. And it tells us how to find the slope of graphs on the xy plane that aren't functions. Like if you had a circle, like x squared plus y squared equals 1, I think you'd agree that at each point it has a slope, but it's not a function. So we don't know how to calculate its slope using everything we've been doing so far. So we have to introduce a new technique to figure that out. And that's what we're going to be covering for the majority of the day on Wednesday. So if that's a lot, don't worry about it. I hope you understood what happened today. That's all I care about. I'll stop sharing my screen. I'll stop recording the video, and I'll just do a little outro for the YouTube channel. That's all for today. Come back tomorrow. I hope you enjoyed this video, and I hope it was helpful.